We will just begin in a few minutes. We'll wait for a few more students to join and then we shall start with today's session. Okay, so let us get started with today's session. So as you all know, the course is over and we have completed all the 8 weeks. Today is just a revision session where we will go over a few concepts and we will try to revise some of the topics that we have learned in the past few weeks. And hopefully this revision session will bring together all your thoughts in one place so that it helps you for your final exam. So today will be a short session actually. It will be only a few questions, 5 questions over here, and then we will actually try to see what we have learned in the previous weeks. So we will go over some of the questions from the previous week as well. So let us get started with the first question for today. Question number 1. So here actually these questions are questions for functions of more than one variable. Up until now we have seen functions of a single variable. Here we will have more than one variable, which is 2 variables to be precise in this case, x and y. So just a few questions on multivariate functions and then we will revise. So the first question, let fx comma y equal 12x cubed plus y cubed plus 12x squared y minus 75y. Then the point 2 comma negative 3 is what we need to find, whether it is a critical point which is a local maximum, or a critical point which is a local minimum, or a critical point which is a saddle point, or it is not a critical point. So as always, I will launch the poll, and please select the option in the Zoom poll. Take a few minutes to solve. Okay, so let us now discuss the solution. So a critical point is a point. Oh, I need to get my pen. Sorry, what happened? Yeah, that's my pen over there. A critical point is a point in which the gradient of the function is 0. So gradient of a function 0 means that the derivative with respect to x is 0 and the derivative with respect to y is 0. This is the notation. Fx means, this means basically del f over del x, and fy, this means del f over del y, and del means partial derivative. So just to jolt your memory a bit, so this is grad f, this notation here, and grad f means del f by del x x cap plus del f by del y cap. It is a vector and these are the x and y components of the vector, and fx is del f by del x. That's the notation. That's the partial derivative of the function with respect to x. And partial derivatives come into picture when you have a multivariate function. So you want to differentiate with respect to one particular variable by keeping the other variable, by treating the other variable as a constant. Now to check for the maxima or minima condition, you need to evaluate this Hessian. It's fxx fyy minus fxy whole square. Fxx, now this means the double derivative of f with respect to y. So fxx actually is del squared f by del x squared. Now fx equals, you need to differentiate. So this is equal to 36x squared plus 24xy. Remember, it is derivative with respect to x, so y is treated as a constant. Fy equals, now keeping x as a constant, so 3y squared plus 12x squared minus 75. Now at the point P, let us call this point P. At P, this is what? Let us substitute the value of x as 2 and y as minus 3. So it is 36 times 2 squared, which is 4, plus 24 times 2 times minus 3. So this is 12 into 3, that's 36, into 4, minus 24 times 2 is 48 into 3, and you see it is 0 because 12 times 4 is 48 and 48 into 3 minus 48 into 3, that is 0. So indeed it is 0. And for fy, it is 3 times y squared, so 3 times 9 plus 12 times x squared, so 12 times 4 minus 75. And if I bring out my calculator, so this is 27 plus 48 minus 75, and this also turns out to be equal to 0. So yes, it is indeed a critical point. P, this point P is indeed a critical point, so option D is ruled out. Now we need to check whether this critical point is a maximum, a minimum, or a saddle point. For that, we need to evaluate this Hessian. So in this Hessian, we need to find out now fxx, the double derivative. So we differentiate this once again. So this becomes 72x plus 24y, and then fyy, this becomes 6y, and fxy this is basically del squared f over del x del y. So first with y and then with x, or the other way, the first with x then with y. So first with y is this, and then with x, this gives you 24x. And if you see that if we do first with x and then with y, then also we get the same answer, which is 24x. Now we need to look at the sign of this Hessian. Okay, so Hessian at the point P is what we need to find out. So it is fxx is this, so 72 times 2 plus 24 times minus 3, that is fxx. Then fyy, that is 6 times negative 3 minus 24 times x, which is 2 whole squared. So I need to pull out my calculator once again. So this is 144 minus 72 times negative 18 minus 24 times 2 is 48. 48 squared is 2304. So now 144 minus 72, that's 72. 72 times negative 18, that's minus 1296 minus 2304. And clearly this is negative, it is less than 0, which implies that this point is a saddle point. So when the Hessian is negative, then that particular point is a saddle point. So the correct option is option C, that it is a saddle point. Okay, so I hope this is clear. Are there any questions? Okay, someone is asking what will be the condition for the maximum or minimum. So condition for the maximum or the minimum, let me write it down over here. I think I have some space. Oh, sorry, there's some space out here. Okay, so condition for maxima or minima is that first the Hessian needs to be positive, and when Hessian is positive, if fxx is positive, then that's minima, and if fxx is less than 0, then that's maxima. It is kind of analogous to one variable. So in one variable, what we have is that the first derivative needs to be 0. This is the first derivative for it to be a critical point, and the second derivative, if that is positive, then it is a minima. If the second derivative is negative, it is a maxima. Here, in addition to that, we have this saddle point. So this is a saddle point. And again, just like in one variable, if the second derivative is also 0, then we can't say exactly what it is. So there is not enough sufficient information. We cannot predict. So these are the different conditions which you can find out by finding out the sign of the Hessian. So I hope it is clear now. Are there any more questions? Okay, so seems that it is clear and we can proceed to the next question. Question number 2. Again, we have a multivariate function of two variables. Let gx comma y equal y to the power 4 minus 32y plus x cubed minus x squared. that the point 1 comma 2 is what? Once again, similar options, whether it is a critical point which is a maximum, or a critical point which is a minimum, or a critical point which is a saddle point, or whether it is not a critical point itself. So take a few minutes to answer. I will refresh the poll once again. Okay, let us now discuss the solution. So this is the question which is similar to the previous one, and once again we need to evaluate the first and second derivatives and the Hessian. So first, let us look at the first derivative. This is partial derivative with respect to x, now with respect to y. Now at this particular point we need to evaluate. So this is 3 times 1 minus 2 times 2, which is equal to negative 1, which is not equal to 0, and gy, this is 4 times 2 square, which is 4 times 4 minus 32. I hope I did this right. Sorry, wait, I wrote this wrong. It's not 4y squared, this is 4y cubed. So 4 times y cubed. Y cubed is 2 into 2, 4 into 2, 8 minus 32. This is equal to 0. So although gy is equal to 0, because this is gx is not equal to 0, as a result this is not a critical point. So the correct option in this case is option D, not a critical point. Moving ahead, let h x comma y equal x squared minus y squared plus xy. Then the point 0 comma 0, which is the origin, is what? A critical point, which is a local maximum, a critical point, which is a local minimum, a critical point, which is a saddle point, or not a critical point. Again, same options, and we need to evaluate based on the Hessian conditions that I wrote in the first question. So as always, I have relaunched the poll, and please try to solve it and select the correct option in the poll. Okay, so time for solutions now. So as always, we will find out all the derivatives and the signs. So hx, the derivative with respect, partial derivative with respect to x, that's 2x plus y. For partial derivative with respect to y, that is negative 2y plus x. At the origin, this is also 0, both are 0, both the partial first derivatives are 0 at the origin, so this implies that it is indeed a critical point. So option D is ruled out. Now we need to find out the Hessian. Now using these, the Hessian becomes this is negative, the Hessian is negative, which implies that it is a saddle point based on the conditions that we wrote in question number 1. So negative Hessian, so we have a critical point which is a saddle point. Option number C is the correct option. Now we have two questions which are slightly different. Question number 4. Let kx comma y equal x squared plus y squared plus 2xy. Then k has, these are the options we need to select, infinitely many critical points which are all global minima, or B, infinitely many critical points of which some are local extrema and some are saddle points, or option C, exactly 4 critical points of which 2 are local maxima and 2 are local minima, or option D, no critical points. The poll has been restarted for all of you. Please try to solve this question. Okay, so now we will discuss the answer. So kx is first derivative we need to find out first. Now both these derivatives are the same actually for partial first derivatives with respect to x and y. Now for it to be a critical point, this needs to be 0. So this means that we get the following condition. And this condition means that there can be infinite possible critical points. So options C and D are ruled out. Now we look at the Hessian. This gives us the Hessian as 2 times 2 4 minus 2 squared 4, which is 0. Now as we know that if Hessian is equal to 0, then we cannot really say. So what we know is that we have infinite critical points, but we cannot really say whether they are maxima, minima or saddle points. So the correct option is that infinitely many critical points, of which some are local extrema and some are saddle points, because we cannot really say which are maxima, minima or saddle points. So extrema, by the way, means whether it is maxima or minima. Both are counted as extrema because they are extreme points. So option B is the correct option. Now we move towards the last question. After this we will revise what we have learnt in the previous weeks. So question number 5. For a box with an open top having dimensions LBH, the volume is V equals LBH and the surface area is A equals 2HB plus 2HL plus LB. So why only LB and not 2LB? Because it is an open top box where L is the length, B is the breadth and H is the height. If V is assumed to be a fixed constant, then the dimensions of the box that minimize the area A are what we need to select from these 4 options. So once again, I will start the poll for one last time in this course. So all of you, please do attempt this poll. This is the last question, not only for today, but for this entire course. Okay, now we will discuss the solution. So area is the following. We are given now in terms of volume, we can write this as the following: H as V over LB, so we have eliminated the variable H from here and written everything in terms of V, L and B. V is a constant. So now this is a function of two variables, which is L and B. Now for extremum condition, the first derivatives need to be 0. So let us look at the first derivatives. Now AL equals 0. This gives the following: now from these conditions we can find out some things. So we have BL squared equals B squared L, which is equal to 2V. So this gives us L equals B, because you cancel out one B from here and one L from here. So L equals B is what we get. And BL squared equals 2V, which implies L equals B. So L cubed equals 2V, which implies L is equal to 2V to the power 1 over 3, which is also the same as B. So option B is ruled out, because for that the L and B values are different. And option C is also ruled out, because for that also the L and B values are different. Now straight away by dimensions I can select option A, because in option A the dimensions for H are proper. It is V over V to the power 2 by 3, which is the dimensions of length. But here this particular expression is dimension means the dimensions are not correct. Here it is length cubed over length, so this is the dimension of length squared. So incorrect dimensions. Based on that, option A is the correct option. But we can actually do better. We can even find it out properly. So we have V equals LBH. So L and B we have found out over here. So that's 2V to the power 1 by 3, that's L. 2V to the power 1 by 3, that's B, times H, which is 2V to the power 2 by 3 times H. So this gives us H equals V over 2V to the power 2 by 3, which is what was there in option A. Now here we can find out the Hessian. To see whether this critical point is maxima, minima or what, or saddle point. So this becomes, so negative 2 times negative 2, so 4V by L cubed. Similarly A, B, B. and ALB is 1. So this gives me the Hessian as following. And we can have means it's actually difficult to determine the sign of this Hessian, but clearly this Hessian is not equal to 0. And we can consider a situation in which H is very large and it's greater than L and B. So in that case we can say that this Hessian will be positive, and what we have is that ALL is positive, so this gives us minimum. So that's how we have solved this question. So this brings us to the end of multivariate functions. We will take a short break of 5 minutes because we are halfway through, and then we will actually revise what we saw, what we have read or studied in the previous weeks. So we'll be back in 5 minutes. Okay, so I hope everyone is back from the break. So we have solved these few multivariable function based questions. Now let us just revise some questions from the previous weeks. So week 1 we had questions on sets and how to write sets. Some elementary questions on limits, and functions. Summations. So we'll just quickly go through these questions. So in sets, you basically write distinct elements. You can repeat the same element as many times as you feel like. So but you actually consider only the distinct elements. So that was this question. Then tangent to a function at a point is actually its derivative at that point. Then we saw how to find out limits. In this simple case, we could actually just plug in the value of x. This is very high school level concept. Speed is distance over time. And these were some definitions of functions. So about a function being injective or surjective. So the definition is a surjective function is an onto function and an injective function is a one-one function. And bijection is both one-one and onto. So onto means for every element in codomain, which is this set B, there is at least one element in the domain that maps to it. So each element in the codomain should actually have a pre-image in the domain. And injection is 1-1, which means distinct elements of domain get mapped to distinct elements of codomain. So if distinct elements of the domain get mapped to the same element in the codomain, then it is not an injective or a 1-1 function. Then again this definition of injective surjective. Then many a times when you have to show some summations and summation of some series, you can actually use this method of proof by induction, wherein you assume that the given statement is true and then you show it for the value 1, then 2, and then k plus 1. And if it is true for 1, 2, 3, so on and so forth, and for k plus 1, then it will also be true for k. And that's how the method of proof by induction works. Okay, so that was about week 1. Let us look at week 2. In week 2 we were introduced the concept of subsets, and basically more about sets, intersection of sets, operations on sets. So this symbol over here, this means subset. So A less than equal to C, or A is a subset of C. And here I made a distinction of being a subset or equal to. So this means subset or equal to, and this means pure subset, means A not equal to C. Then we had this definition of brackets, open brackets and closed brackets. So parenthesis is open bracket and square brackets are closed brackets. Open bracket means that that particular element is not included, and closed bracket means that the element is included. This backslash means the operation of difference. So our backslash, the set 0 to 1 means set of real numbers minus the interval, closed interval 0 to 1. Then you can represent sets in two different forms. Either you can list down the elements, or you can write down the rule that gives those particular elements. Phi denotes the null set, that means it is empty, it has no element. Then these are like Venn diagrams, and Venn diagrams are useful for visualization of sets. And this symbol N denotes the cardinality, which is number of elements. And this is union operation A union B, which means that all the elements of A and B combined. So this is one identity of cardinality for A union B. Then this is triangle inequality. Okay, so that was about week 2. Let's see week 3 now. So in week 3 we formally saw how to evaluate limits, and then we solved these questions on limits. So in limits, one of these tricks is here to make a substitution. This is what we have seen in question number 1. And basically making use of properties of limits. And one important rule for evaluating limits is the L'Hopital's rule. It works for either 0 by 0 form or infinity by infinity form. So when you plug in the value of the element of which the limit is being taken, so if you plug in that value of the element, and if you see that the numerator and denominator both go to 0 or they both go to infinity, then you can make use of this L'Hopital's rule. And what it says is that it's given over here. So limit x tending to y alpha over beta when both alpha and beta tend to either 0 or infinity when x tends to y is the same as limit x tending to y d alpha over dx over d beta over dx. So derivative of the numerator with respect to the variable and derivative of the denominator with respect to the variable. You will take that and then plug in the value to find the limit. So here the definition of convergent and bounded is given. So if there is a sequence and as you go further and further in the sequence, if the limit converges, then it is a convergent sequence. And the sequence is bounded if it has lower and upper bounds, like each of the elements of the sequence are within a particular interval. So in a function, one particular value element in the domain cannot have two images in the codomain. So for a function to be like for fx, if there is one particular value of x, then fx cannot take two different values. If it does, then it is not a function. Okay, so that was about functions and sequences and limits. Sorry. Moving on to week 4. So in week 4, we were actually introduced to some concepts related to economics. And then we were applying the concepts the mathematical concepts that we have learned previously to these problems involving economics. Oh, sorry, I don't need the keyboard. So one important term that we saw is this epsilon d, which is the elasticity of demand, and this is the price demand equation that we have, and based on this price demand equation, this is how we find the elasticity of demand. And then roots of a quadratic equation, this is also basic mathematics. Equilibrium is when demand equals supply. This is elasticity of demand, defined over a price interval. And these are the possible conditions on the elasticity of demand. Elasticity of demand is always negative, it's less than 0. If it is less than 1, then it is less than -1, it is elastic. If it is equal to -1, it is unit elastic, and if it is greater than -1 but still less than 0, it is inelastic. So break-even condition is when profit is equal to 0. Week 5. Again, more about limits and using the L'Hopital's rule. We have already seen the L'Hopital's rule and the condition under which the L'Hopital's rule can be used. So once again, either 0 by 0 or infinity by infinity form, you can use the L'Hopital's rule, in which you differentiate both the numerator and denominator with respect to the variable and then find the limit. So it is a very handy rule actually. Then convergence. Then we also saw the concept of left hand limit and right hand limit. So for a limit to exist, both the left hand limit and right hand limit should exist and should be equal, and that value is actually the value of the limit. Then we saw piecewise definition of functions, and one simple example is this mod x function. Okay, so that was about week 5. Week 6. In week 6, we were introduced the concept of differentiation and differentiability. Again, for differentiability, both the right hand derivative and left hand derivative should exist and should be equal. And here we have composition of functions. So FOG is actually composition of two functions. FOG means f of g of x. So first you apply the function gx, and then on that result you apply the function f. So that is what this FOG means. So first you apply g and then you apply f. Similarly, GOF would mean first you apply f and then you apply g. Then we have definitions of marginal tax rate, which is derivative of the tax function. Then average tax rate, average cost, marginal cost is the derivative of the cost function. Once again, the elasticity of demand. Now week 7, the penultimate week. Here we saw minima and maxima of a function, both local minima maxima and global minima maxima. So note that local maxima need not be the global maximum. Global maximum is the absolute maximum of the function, and local maximum is within a small interval, it is actually the maximum. And the condition for finding minima or maxima is that you take the derivative of the function and set it equal to 0. Then the second derivative of the function at that particular point at which the derivative is 0. If the second derivative is positive, then it is a minima. If the second derivative is negative, then it is a maxima. And then you have to check whether it is local or global by looking at the entire range. So here is a simple example. I have shown what local maxima looks like, what local minima looks like, and then absolute maximum and absolute minimum. Finding local maxima, so you take the function, you find the derivative of the function, you set the derivative equal to 0 and find the roots. Then you find the second derivative and at the value of these roots where the first derivative is 0, you find the sign of the second derivative. If it is negative, then it is a maxima. If it is positive, then it is a point of minima. Once again, average cost, total cost, marginal cost, the revenue, the profit. And then to maximize the profit, we find the derivative of profit. To maximize the revenue, we find the derivative of revenue. Marginal revenue, this is once again derivative of the total revenue. And finally, week 8, the last week. Here we saw points of inflection and concavity and convexivity of functions. Okay, so let us just see. So point of inflection is when the second derivative is also 0. And here is a graphic which shows what a concave and convex part of a function looks like. So if the second derivative is negative, then that is a concave region. If the second derivative is positive, then that is convex region. And the sign from concave to convex changes at the point of inflection where the second derivative is 0. So here I have defined point of inflection where the second derivative is 0. Second derivative 0 means point of inflection, and that is the point where a function from concave becomes convex or vice versa. Okay, so that's all from my end. We have looked at some multivariable function questions, and also we have revised questions from the previous week, and we have basically skimmed through the concepts that were introduced in this course. We looked at it cursorily, and I hope this revision is sufficient for all of you to give the exam. All the best for your final exam, and I hope all of you do well. And let's hope we meet in some other NPTEL course in the future. So that's it from my end, and the lecture is over, and this is our last session for this course, and now you have only the final exam left. Okay, so bye everyone. See you. Yeah, so thank you for joining. Do well in your exam, and all these videos and all these lecture notes have been uploaded. So the link to the videos, I'll put it up in the Zoom chat box. That's the link to the YouTube channel where all these problem solving sessions have been uploaded as live streams. And these lecture notes are also uploaded in a folder, and the link to the folder will be available in your course portal. So you can download the PDF of these lecture notes. And if there are any questions, feel free to ask in the course portal, or you can ask in the YouTube channel as a comment to the video. Hope all of you learned some new concepts in this course. And for those of you for whom the course was not new, I believe it helped you revise some of your concepts. Okay, so bye everyone. You can now leave the Zoom meeting if you do not have any question. The session is over from my end.